Today, week 13, Tuesday lecture. The agenda we're going to do for today's class is on ductile U criteria. Okay, so there are two general types of ductile U criteria. Okay, so before I go on, what is the purpose of the U criteria? Okay, so the U criteria is used to determine the transition between elastic behavior or elastic to plastic behavior of materials. Okay. So that's why you criteria. So the next thing is, what do we mean by ductile? Okay, what do we mean by ductile first? Okay, so ductile material, excuse me, or in our case, metallic material are materials that the stress yield is so much less than the stress ultimate strength. Okay. So if we look at brittle material, in brittle material, right, the stress yield is approximately equal to the ultimate strength. Okay, so that's where we classify. So this criteria that we're going to do is only for ductile material, not for brittle. So there are two commonly used yield criteria for ductile materials. And we're only going to learn one due to time. So the first one, which we are going to learn in detail, is the maximum shear stress criteria. So it's commonly known as Tresca. Okay, so there's a maximum shear stress criteria. And the other one, the second one, which we will not learn in detail, is known as the maximum distortion energy criteria, which we usually call it as von Mises. Okay. So as I said, we are going to focus on the maximum shear stress criteria due to time. So let's look at the maximum shear stress criteria. So which is normally known as Tresca, okay? And you see, Tresca actually is spelled with T. I do the tau down here. This is to remind me that this is shear stress. Okay, that's how I remember Tresca is also always shear stress. So the first thing with Tresca criteria is tau max experimental, okay, is equal to stress yield divided by 2. Okay, so this is the first equation for Tresca criteria, where stress Y, capital Y, is the yield strength. Okay, so this yield strength over here, what you see is a material property. And then you will see tau max E. So we will define this as shear stress or maximum shear stress. Obtained from experiment. Okay, so basically it's a material property. So if you look at a material handbook, okay, or material data, so which I have upload this on Avenue to Learn. It's just a table. So this is a typical table you'll see in a material handbook, right? And I want you all to pay attention to this, okay? So what you usually see is you have, or what this table shows is you have material classification on the first column. Then you have density, and usually what they will show is the ultimate strength. You see the ultimate strength. And then the ultimate strength, they'll tell you how the tests are carrying out in tensile, compression, or in shear. So in terms of normal stresses, okay, what you see over here, these are all your normal stresses. This is also your normal stresses. So the normal stresses are the principal stresses over here. Okay. Then the next column you see is your yield strength, which we will use this data more frequently than ultimate strength during ductile. So what you see is you have tension and you also have shear. Okay. And you will see most of the time you have the values in tension and very limited data on shear, which is the reason why is because most tests are carried out in uniaxial tensile tests. Okay, very limited are carried out in shear because of cost. Okay, and then you have the fourth column is your Young's modulus E and your modulus of rigidity G, thermal coefficient of thermal expansion, and then ductility. Okay. Now, what happens is if you don't have data over here, right? You don't know any of this. You can have a intelligent guess, okay, using Tresca criteria. So let's pick an example. So let's say ASTM. We have ASTM A992. right? So for this material, we are given stress yield, right, is equal to the 992. Stress yield is 345 megapascal. Okay. So you can also state that using Tresca criteria, tau max is equal to stress yield divided by 2. Right. So 345 divided by 2 is 172.5 times 10 to the power 6 Pascal. You can declare that. Okay. Because doing all these tests is not cheap. Okay, so you can use a certain criteria. So let's do the obvious. If we were to look at the structural, okay, structure ASTM A36, you can see that the stress yield is equal to 250, okay, megapascal. So if you use Tresca, right, so the tau max will be equal to 250 divided by 2, right? So 250 divided by 2 will be 125 times 10 to the power 6 Pascal. But when they have done the experiment, okay, so from experiment, right, tau max E is equal to what? 145. Right? So it's better to be using a criteria that is lower than the what? The experiment. Okay, and it's true, right? For the fact that it's well known that the Tresca criteria is more conservative. Okay? It is well known. Okay, so it's more conservative. As you can see from experiment, we get 145 megapascal, whereas using the criteria is only what? 125. It's well known that Tresca is more conservative. Now, Tresca's criteria, right, I've written earlier, is equal to stress yield divided by 2, which is the experimental value. Now, based on tau max analysis, okay, so based on tau max A, right, is equal to half of your stress max. Okay, and this is our equation 2. So when do we apply equation 2? Now, this is based on analysis. Yeah, this is not based on material properties. Okay, this is doing your analysis. So I'll define here. So tau max A is your maximum shear stress obtained from structure analysis. Okay. So when can we use equation 2? Okay. So equation 2 can only be used, okay, when